A gun-type fusion reactor. Fusion power usually means giant reactors, magnetic fields, and temperatures hotter than the sun. But there's a simpler idea, one that looks more like an engine than a power plant. What if we fired a high-speed projectile into a nuclear fuel target, like a piston slamming into a cylinder, to trigger a burst of fusion? This is gun-type fusion, simple, repeatable, and maybe the closest thing to a true fusion engine we've ever imagined. How it works. High energy impact. Gun-type fusion is based on impact. A solid projectile is fired at high speed into a small fuel capsule embedded within a mixed material pellet. The pellet sits inside a sealed reaction chamber surrounded by layers of shielding, coolant, and pressure control systems. The fuel inside the capsule is a deuterium-tritium mix, a common choice for fusion. When the projectile strikes, it starts the chain. A violent, precisely timed compression begins. How it works. A precision shock wave. That impact creates a shock wave, and the timing has to be perfect. The wave travels through the pellet, compressing the fuel in just billionths of a second. If the shape and pressure are tuned just right, fusion begins. The atoms combine, releasing a burst of energy, a helium-4 nucleus, which is not radioactive, and a high-energy neutron. Almost all the energy goes into that neutron. When the neutron slams into the lithium coolant lining the chamber, it generates heat, and also produces fresh tritium. That tritium is captured as a gas and processed into new fuel pellets. The heat from this reaction drives turbines and generates electricity, just like in a conventional power plant. What temperature is needed? When people hear fusion reactor, they think of extreme heat, and that's true. Tokamak reactors like ITER are designed to reach up to 250 million Kelvin, using magnetic fields to hold the reaction steady. Laser fusion systems like NIF use power pulses to hit around 100 million Kelvin. Gun-type fusion reactors target a similar range, but reach it using a physical projectile and shock compression. And for perspective, the core of the Sun fuses at just 15 million Kelvin, thanks to the crushing pressure of gravity. Fusion using deuterium and tritium can begin around 100 million Kelvin, but the reaction probably peaks much higher, closer to 700 million. Gun-type systems aim for the lower range and rely on pressure and timing to make up the difference. What pressure is needed? We often think of fusion as needing extreme heat, but pressure is just as important. In the core of the Sun, gravity generates around a quarter of a terapascal, enough to fuse atoms over millions of years. Tokamak reactors like ITER use magnetic fields instead of pressure, operating at just thousandths of a terapascal. Inertial fusion systems like NIF compress fuel pellets to around 30 terapascals, millions of times more pressure than Earth's atmosphere. For gun-type fusion to break even, we need similar conditions. Our estimates show that a 0.2 milligram fuel pellet burning for 10 nanoseconds would need about 30 terapascals of pressure. If the burn time drops to 5 nanoseconds, the required pressure jumps to around 60 terapascals. Technical challenges. Gun-type fusion may be simple in concept, but there are many variables that must be exact. To get fusion, a small metal slug has to hit the target at over 20,000 meters per second. That target contains a tiny fuel capsule, often less than a millimeter wide, and the impact must strike at the perfect angle. Inside, the pellet is made of layered materials designed to focus the shock wave, and the shape of that wave must be precisely tuned. Too slow and you don't reach fusion pressure. Too fast or off axis, and the compression symmetry breaks. And because the shock wave passes through multiple phases of matter in just a few nanoseconds, solid, liquid, plasma, and beyond, modeling the process sits at the bleeding edge of physics. Getting everything right and repeating it shot after shot is the real challenge of gun-type fusion. Cost per megajoule of output. First Light Fusion is a UK-based company developing gun-type fusion, using high-speed projectiles to compress fuel and trigger fusion. This chart shows their cost per megajoule of fusion output over the last 3 years. Instead of projections, we're using actual numbers. How much money has been spent, and how much fusion energy has been produced. In 2022, they reported a 4.5 megajoule fusion shot. With about $95 million invested at that point, their cost per megajoule was just over $21 million. In 2023, there were no new energy results, so the numbers stayed flat. In 2024, they announced a new pressure record, but without additional confirmed energy output. With cumulative investment now at $105 million, the cost per megajoule drops to $11.6 million, assuming the same 4.5 megajoule output for that second shot. For context, the market price of energy today is around 10 to 20 cents per megajoule. So while First Light's design is promising, this chart shows they're still in the early stages of development with a long way to go. Gun-type fusion highlights. We've analyzed all the major factors. We've looked at the core design, the physics, the temperature and pressure requirements, and the prototyping cost to produce test energy. Gun-type fusion stands out for its simplicity and relatively low cost. The design is compact, the materials are basic, and the approach avoids massive infrastructure. But under the surface, it faces some of the toughest technical problems in fusion, from nanosecond timing to shockwave symmetry to extreme compression physics. With only one confirmed energy shot so far, it's still early. Whether this becomes a serious contender or just a clever idea that hits a wall is something we'll have to wait and see.